And the next speaker is Daniele Dorigoni on modularity and resurgence of N=4 integrated correlators.
Let me keep an eye out. You're going to tell me when.
Yes.
Fantastic. Thank you, Tuan. All right. Thank you for organizing such a fantastic conference. It's also great to be on the first day so I can relax and listen to all of the physics you guys are going to tell me about. I will be telling you about some works I've been doing recently. Started out with a bunch of works with Concau Wen and Michael, and then we picked up more amazing collaborators. Haitian, who's just a master's student, is going to go to Harvard for his PhD. And then Fernando, who should be here, but probably not yet. Shai as well. Paolo Vallarino, who's in the audience, I've seen. And then Rudolf is my current PhD student. He's going to go as a postdoc in Parma, eating a lot of prosciutto, so that's going to be great. And when I'll finish, I'm going to tell you some work in progress I've been doing together with Giao, Daniele Pavarini, Concau, and Haitian. In total disregard to what Ben just told you, I'm going to focus on one theory. N=4. Sorry, Ben. Actually, there's a lot of them. They're parameterized by a coupling constant, as we already heard. I'm going to write it in here because I'm going to, Agoromo, great choice. The coupling constant, which I put into a complex form, is the theta angle plus G and Mills. And this is really the only data you need to give me to specify this beautiful theory. Well, you actually need to give me a gauge group, which for most of the talk is going to be SUN. I'm going to tell you every now and then when I'm going to deviate from that. And the reason why I like this theory is that it's beautiful. It's one of the few theories where we can compute a lot of stuff exactly. It has nothing to do with LHC, but is a lab for exact stuff. So what are we going to be considering here? We're going to be considering particular correlations. And which correlation functions are we going to be considering? Well, there's a lot of fields in N=4, but in particular it has 6 adjoint scalars. And the reason why they're nice is because you can package them into this bilinear. We don't like working with indices, so we put some null polarization vectors for their symmetry, and this operator is called O2. Is a protected operator, is dimension 2 period, no corrections. And the reason why it's nice is, besides being a half BPS, is that it sits in the same multiplet as the stress energy tensor. So I'm going to mention shortly that knowing stuff about this guy will tell you stuff about gravity. But it's way easier. It's a scalar, and it's protected, sometimes also called 0, 2, 0. Although it's protected, its 4-point function most definitely is not protected. So if you take O2, 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 you have some factors which you can actually fix uniquely by superconformal invariance. Some are symmetry dependence, some space-time dependence. But then this factor in here, which is schematically denoted as T, it has a lot of interesting stuff. It's a non-trivial function of the crossing ratio, U and V. It depends most definitely on the coupling constant, and it most definitely depends on the gauge group. Now, if you're a bootstrap person, if you ask Balt, this is what is really hard to compute. We don't know how to compute it exactly. And the reason why it's interesting, as I mentioned, is that knowing this object in turn will tell you stuff about the stress energy tensor, which in turn, in the dual theory, will tell you about graviton amplitudes in type 2b. So this is going to come back later on. And there are other ways of computing graviton amplitudes. Here, if you were really to do in string theory, you could be doing some genus expansion. And apologies, I realized later on, but if you like your donuts with more than 2 holes, do go to Oliver Schlotterer's talk. He's going to be talking about what to do from him onward. It's very difficult. We're going to be bypassing that altogether. So, how do we get a handle on these correlators? And why, in the title, there is integrated correlators? Well, to this audience, probably I shouldn't even put this slide, because if you know what localization is, there is no need. If you don't know it, you're not going to learn it, but I'll do it anyway. So, localization is a great tool, thanks to Pestun, to actually bypass completely having to compute a path integral. Path integral, very ill-defined. Matrix model integrals, way better. So what do? We deform slightly the theory. We introduce a mass parameter. This breaks supersymmetry. That's called N=2 star. And although this theory is less supersymmetric, we can still compute its path integral as a genuine matrix model integral. So you see here that the path integral of this theory with gauge group G, mass parameter M, and coupling constant tau is given by this matrix model. I'm not going to tell you the details. I just want you to highlight in here. There is some classical action. There is a perturbative part. This encodes all of the one loop determinant fluctuations. And there is a beast in here, which is usually way harder to compute. It contains all of the instantons. That's called Nekrasov partition function. But the bottom line of this slide is that instead of computing a path integral, we are going to be dealing with a matrix model. Way easier, although it's very hard, way easier to deal with it compared to a path integral. And what do? Well, thankfully, we have introduced a mass parameter, so we can take derivatives with respect to parameters. Now, in here, we can consider two objects. One in which I take a Laplacian with respect to the coupling constant, and two mass derivatives to the partition function. Now, forget where this is coming from. I give you a path integral, you take derivative. What's going to happen? You bring down whichever operator is attached to that parameter. So not surprising here, I'm going to be bringing down 4 operators. In here, I'm taking 4 mass derivatives, I'm going to be bringing down 4 operators. I then set the mass to 0, so I go back to living in n equal to 4. What is way harder to see, and thanks to the work of Binder, Chester, Pufo, and Wang, and then by Shai and Silviu again, these particular combinations of 4 derivatives are actually 2 4-point functions of the same O2, 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 O2 I told you before, but integrated against 2 very specific measures I was too lazy to write out. This is a very easy measure. You can write in terms of the conformal ratio. This is slightly harder. If you know what it is, this is called usually D1111. It's a box diagram. But this is a very specific measure. So by computing these quantities, which I call C and H, you will get not quite a 4-point function. That would be great. You're getting these integrated 4-point functions. The other thing I'm going to mention towards the end of the talk is that you can actually also get integrated point functions where you insert some defects. So this was recently discussed by Pufo, Rodriguez, and Wang, and then by the Italian gang below, Francesco, who's somewhere in here, Frau, and Lerda. You can consider, rather than the partition function, a Wilson loop insertion. And again, you play the same game. You take 2 derivatives. This is going to bring down 2 operators. You're left with this 2-point function of 202 in the presence of a half BPS Wilson loop on the equator. So these are the 3 objects I'm going to be considering. First, second, and defect. The reason why I call them first and second is because I study the first and the second second. There is nothing special. It increases, this is the easiest, these 2 are way harder. But the key message, and then you can go back thinking about lunch and soup, is the fact that electromagnetic duality, if you wish GNO duality, is so constraining that you can compute this object exactly. Although the correlators themselves are very hard, these objects will display some beautiful modular structures. And they're going to give you some non-holomorphic functions of the coupling constant tau, and surprisingly, which is completely non-obvious from this matrix model, they will actually be lattice sums. And they will have some nice properties under modularity. The first 2 objects are actually modular invariant functions. The third one I'm going to mention later on how electromagnetic duality acts on it. So cool. So let me start with the first. So this is the particular combination of derivatives that we act on the partition function. What did we find? We found an exact formula for this 4-point function integrated, which is valid for any gauge group. It's valid for any value of the coupling constant. And, importantly, it transforms as it should under electromagnetic invariance. So we started out on the classical side with Michael and Concau. We're using some key results by Chester et al. And also by Fernando, Chester, and Tobias, who also should be in the audience, but I haven't seen anyone. And we concluded the story with Paolo, studying the case where G is an exceptional gauge group. This is a little bit harder, and I'm not going to tell you anything about that, I'm afraid. But just to show you how it is, this is that 4-point function integrated in the case of SUN. It's a sum over 2 indices, M and N, 2 integers, some modular invariant Borel-like factor, and some functions, B and T, which are just some rational functions. This can be written very explicitly in terms of Jacobi polynomials for SUN. And just to give you an idea of how easy it is, this is the only data you need to give me for the SU2 integrated correlator. Very simple polynomial. As I mentioned before, in the case where the gauge group is, well, not SUN, this formula is a little bit different. Interestingly, in the case of exceptional gauge group, S-duality is not SL to Z, gives you something which is called freak involution. This is something that we studied with Paolo. But for me, this formula, if you check what the matrix model looks like, is very unexpected. And it's modular invariant, and it's extremely simple. So we can check few things. First of all, you can compute SU2, SU3, SU4, and you can compute it in perturbation theory. Surprisingly, you will get an asymptotic expansion when tau2 is large. Remember, tau2 large means G and mil small. So compute diagrams if you wish. And this is actually what we have computed at 2 loops. And then Kong-Kao and his former student Zhang, who should also be in the audience. And if you care about multiple zeta values and how this calculation is done, do go to his talk on Wednesday, I believe. You can also take this 4-point function. We know it up to, I believe, 5 loops. Gets harder and harder and harder. You put the measure I didn't tell you, you integrate, and you will find match. Another way of looking at this object is from the point of view of the spectral decomposition. So this has ties with holographic ensemble averages. This is something that Scott Collier and Eric Permuter did. One way to look at it is by expanding this expression as finite n in this sort of formal object. You get this object E, which is called a non-holomorphic Eisenstein series. I'm going to tell you some more details later on, but for the experts in the audience, this formal object in here, you can actually write it in terms of this spectral decomposition. And importantly, there are no mass cast forms, which is something that appears quite a lot, for example, in the context of chaos. And again, just to show you how easy this integrated correlator, if you write it in terms of this spectral decomposition, the only data you need to give me is this function. For SU2, this function is just this polynomial. The 4-point function itself, extremely hard. This integrated correlator, so much easier. Now, a couple of words, because this is usually not well known. So probably you've heard of Eisenstein series. Those are usually modular forms. These non-holomorphic ones, also called real analytic, this paper chap in here, that's Eisenstein. They are non-holomorphic modular invariant functions. And importantly, they have 2 perturbative terms. Remember, tau2 is just G and mils. Xi is the complete Riemann zeta, and then everything else in here are instantons. Tau1 is the theta angle, so this you can really see it as an instanton expansion. And now sigma, it appears always in here, is a sum over divisors, and k is a Bessel function. So these objects play a key role in the finite n version of this integrated correlator, but actually they also play a key role in the large n expansion. So that's the second thing we did. From this lattice sum expression, we can do something which is not the 't Hooft limit. Usually, we don't have expressions for finite n and finite tau. We can do 't Hooft limit. In here, we have an expression for finite n and fixed tau. So we can do a larger expansion where tau is kept fixed. And this object splits into 2 terms. A perturbative series. You see in here that it has a power series in n is large, whose coefficients are non-holomorphic functions of tau, and some non-perturbative terms in n, which are going to be exponentially suppressed in n. So let me start with the easy stuff, perturbative. So at large n, the expansion of this integrated correlator changes dramatically. You get, order by order in 1 over n, a finite number of the same objects I told you before, this Eisenstein series, with half integer indices, 3 halves, 5 halves, and so on. Why is that? Well, this ties up to what I told you before. At large n fixed tau, you can actually match with type 2b. In this case, tau is not theta and g and mils. You can interpret it as the axiodilaton, chi plus 1 over g string. And of course, n gets mapped into alpha prime and the size of the area space. So what is this large n expansion? Well, this is just an effective low energy expansion in type 2b. To the order n to a half and n to minus a half, you can actually match them with a coefficient that were found long ago by Michael and collaborators, and Pierre as well, who's here, Again, I should not put this last paper in here. It's going to appear later on. These are higher derivative corrections in type 2b. R to the fourth, V4, R4. These coefficients are precisely E3 halves, E5 halves. So you can really reconstruct from the large N fixed tau type 2b at low energy. This other object will appear shortly. It's not an Eisenstein series, and in fact, it does not appear in here. What about the non-perturbative terms? Well, again, since we have an expression for all N and fixed tau, we can also do non-perturbative. So we can rewrite the perturbative part as a sort of genus expansion, but now there is still tau. This is not in terms of lambda. If you expand at large N, a fixed genus expansion, you find an expression which is a power series in N, whose coefficients are this non-holomorphic Eisenstein series and some factorially growing coefficients. For example, in here I show you the genus 0, 1 factorial, 2 factorial, minus 1 factorial. That's an asymptotically divergent series. So what did we do with my student Rudolphs? We constructed a modular invariant way of performing a Borel-Calvert summation. So from this asymptotic series, we can prescribe a way of resumming these factorially divergent terms and obtain out of perturbative data non-perturbative physics. In this way, the large N non-perturbative terms, we were able to write them as an infinite series, again, of perturbative corrections in N times some new modular invariant objects. This modular invariant object takes this form. You see immediately that there is an e to the minus root n. These are exponentially suppressed in N. However, this lattice sum combination, if you play a little bit with modular forms, is immediately a modular invariant object. So we found a non-perturbative modular invariant large N completion. So these objects here, we never found them before in the literature. They also arose later on in the context of the large charge expansion of OP. They are higher charge operators by Hinek, who's here somewhere, and Eric and Raj, and as well by Konkao and his two students, Gus and Xi. And also in a completely different context in terms of toroidal energy in 3D by Ifan and Duo. Importantly, since this object is at finite tau, we can also, at this point, retrieve the tooth limit. But you need to be careful. You can actually retrieve two different types of tooth limits. The one in which you keep the standard tooth coupling constant, or the one in which you keep the dual tooth coupling constant. These modular invariant terms now split, and they will give you non-perturbative terms coming from F-string, worldsheet instantons, or something related to dionic instantons. And these modular invariant corrections contain all of the resurgence results that we have found by studying the large lambda asymptotic expansion or the large lambda dual asymptotic expansion. So they really contain everything. And we can also understand them holographically because they're coming from PQ string instantons. You just need to use the holographic dictionary, and these exponentially suppressed terms I told you, they look like 4 pi L squared, with L the radius, times little l, which is just telling you how many copies of a PQ string you put. TPQ is just a string tension of a PQ string. So you can really think of them as coming from coincident, L-coincident PQ string warp instanton for a string wrapping a great S2 instead of S5. So for the first integrated correlator, everything works nicely. We can do finite N, large N. For the defect and the second, as I mentioned, are way harder. So I'm going to tell you a few things about this second integrated correlator. And it's something that we studied with Fernando Aldai, Shai Chester, Michael, and Konkao. So you just do something very similar. You take 4 mass derivatives. This gives you still the same 4-point function. You just integrate against another measure. So far, we only have exact results at large N. And the large N expansion splits into, some constant term, some half integer powers in N, which looks very similar to the first integrated correlator. Just Eisenstein series, nothing else. But we can still use this modular resurgence to extract the non-perturbative terms coming from this series. The novelty is really here, this HI. These contain integer powers in 1 over n, and, crucially, it's not given by Eisenstein series. It is given by something else, which terribly are called generalized Eisenstein series, which tells you absolutely nothing, because generalized can mean anything. However, the key point is that this object, this E, is now depending on 3 parameters. S tells you the eigenvalue with respect to this operator, and S1, S2 tells you the sources. So these are modular invariant solutions to this inhomogeneous Laplace equation, whose sources are the Eisenstein series we saw before. Now, this object had already appeared, again, in the coefficient that I told you before it was missing. So Michael, Steve, and Pierre studied this D6R to the 4 correction in type 2B and found that the coefficient is precisely given by one of these objects. However, string theory, wait, I thought I had half an hour.
Sorry?
I thought I had half an hour.
25 minutes plus discussion.
Cool, all right, speed run. Thank you.
There's no higher correction.
Perfect. Good, so to keep the story short, although these objects do not have a lattice sum, what we have found is that the way they appear in this integrated correlator is through this more complicated lattice sum, which is actually constructed out of some object that Don Zagier introduced because Michael asked him to. So it's in unpublished notes, of course, as it happens, and they are constructed from these modular local harmonic mass forms, if it tells you anything. Importantly, one by one, these objects contain in their asymptotic expansion, so instanton and so on, they contain weird numbers, L values of holomorphic cusp forms. String theory does not like that. You're never going to find combinations of these objects for which these L values survive. String theory always selects some combinations of this object for which these L values drop out. This is something that we saw in the context of genus 1 amplitude with Axel, Kleinschmidt, and Oli. And mathematician Kim Klinger-Logan, Ksenia Fedosova, and Danilo Radchenko studied from this point of view of the second integrated correlator. The thing that links the two correlators together is this set of mysterious Laplace equations. We take another Laplacian with respect to tau. Now you would think that you're dealing with a 6-point function. As it turns out, you don't. You can see that it's the same 4-point function where you change the number of colors. For the second integrated correlator, the Laplacian is again not a 6-point function. It talks with the same correlator and with the first. And the same for this integer part. We don't have it fully under control, but if we take the Laplacian on the integer part and focus only on the Eisenstein series, we find the first correlator square. We don't know why that's the case. Good, so in the last 4 minutes, let me tell you a few words about the integrated correlator. So, local operators are not the end of the story. There's also extremely interesting extended operators. Wilson lines, for example. In QCD, they're extremely important. They tell you confinement, deconfinement. And in n equal to 4, they've been studying recently because they will tell you about the scattering of gravitons from brains. So, the kind of correlators that we are considering are the easiest one. They're just parameterized by an electric and a magnetic charge. P and Q co-prime integers. Now, if you give me an electric charge and no magnetic charge, that's called a Wilson loop. If you give me a zero electric charge, magnetic charge, that's a toothed loop. However, crucially, under electromagnetic duality, now not only you change the coupling constant, but you need to change the labels P and Q. So what did Pufu, Rodriguez, and Wang, and then Bill Loga, Vanyo, Frau, and Lerda study is this integrated correlator where you put a Wilson line. Now, under modularity, you expect tau to change, but also the nature of the defect. So if you take the Wilson loop and you act with an SL2 on tau, this will give you the PQ correlator, where P and Q are just the last row of this matrix. For example, if you do an S duality on the Wilson loop, you'll get the tooth loop. So, in this soon-to-appear paper with Xiao Duan, Daniele Pavarini, Haitian Xi, and Poncao, we have studied this integrated correlator. And we have found, again, a lattice sum representation. This was constructed in terms of novel automorphic forms. Now, you're not dealing with modular invariant objects. You need to give me an object that depends on tau and some electromagnetic labels. Once you change tau, the electromagnetic labels Q and P have to change accordingly. Now, I just flashed this. Only because if someone has seen something of this form, I would be very happy to chat with. I discussed with a bunch of mathematicians, and they never really appeared. So, or unless I completely missed them. But this object, crucially, they have the correct transformation properties. If you take one of these building blocks for a PQ defect, and you transform both the coupling constant and the charges, these objects are covariant. So we have been able to predict, for example, the toothed loop defect integrated correlator, something that otherwise is extremely difficult to compute. Actually, I believe There are some calculations using localization, but they're extremely hard. So in our way, once we have found the right space of modular objects, we can predict them for free. Good, so I'm done. Let me just conclude with a bunch of words. So I hope I convince you, or at least I try to convince you, on how powerful modularity is, broadly intended, not necessarily modular invariance. In this case for integrated correlators, requiring some sort of automorphic properties fixes them completely. Although the correlator themselves, remember, these 4-point functions or the 2-point function with a Wilson loop, they're not protected. But somehow this integrated correlator picks out some beautiful, simple part. This has also been extremely useful in the context of Bootstrap. Because the 4-point function I told you before, this is something that you can try to compute with the Bootstrap. The integrated correlator gives you extra constraints. So this is something that Shai will talk about, I believe, on tomorrow. That's Shai. He's not here. And he has done 2 works, so I believe what he's going to be talking about is precisely the role of this n=4 integrated correlator. But there's also some works in n=2. However, there's been quite a lot of extra activity on other type of integrated correlators. So with Michael and Kwon-Kao, we study higher point functions, what are called maximal U1 violating. So these are higher than 4-point function. You scatter 4 gravitons with dilatons as well. These are modular forms. There's been higher charge operators as well, as I already mentioned. I believe Francesco, who's here, I've seen him before, is going to be talking about this giant graviton expansion, another type of integrated correlator related to D-branes. And finally, there's been also results in n=2. And again, I believe Paolo will be talking about this. There's been quite a lot of work. I apologize, I should have also put in here a bunch of work by Paolo and Alessandro Pini, who's also here, and they've been working a lot on n=2 integrated correlators. So there's quite a lot of stuff. Finally, with some open questions, and then I'm done. So as I said, for the second integrated correlator and for the defects, so far we haven't really the same systematical approach that we had for the first one. For the second integrated correlator, we only know at large n. For the defect, we are understanding the finite n, so we can see exactly n=2 and n=3, but we don't have a systematic for all n. All of these lattice sums and differential equations, I really don't know where they're coming from. There might be some 2D for this story, but so far we haven't really understood what it is. For the more mathematicians in the audience, but Ben said that there shouldn't be any in here, but there are. Why does string theory only like multiple zeta values? It only selects forms and functions whose asymptotic expansion contains very special classes of numbers, what are called single-valued multiple zeta values. And finally, this is way more open, how far can we push this integrated story? Of course, we would really like to get a handle on the unintegrated part, but that's of course very hard, so it's not really clear how much this integrated story is buying us, but it is buying us quite a lot. So with that, that is all. Thank you for your attention. Everyone's very hungry.
So you talked about the Eisenstein series and the generalized Eisenstein series. So correct me if I'm wrong. So Eisenstein series appeared only because you were talking about the eigenfunctions of the Laplacian?
Very good. Well, I would say that the argument is the opposite. So there is no reason why they should appear. Okay. But the fact that they appear and the fact that they are solution to the Laplacian suggests that there should be some Laplace equation behind. Okay. There is no reason a priori to expect that the action of the Laplacian on this integrated correlator should produce anything particularly simple. Yeah.
Right. So is it true that this generalized Eisenstein series are eigenfunctions of some generalized Laplacian?
Not really, no. So they're really solution to an inhomogeneous problem. So that's the problem they are solution of. Very good. You see that there is the Laplacian minus eigenvalue, but then the sources are this Eisenstein series. So these objects in here themselves, the generalized Eisenstein, they are not lattice sums. These on the right-hand side are. So this is a sort of, there is a notion of depth, which tells you basically what type of numbers are appearing. In an Eisenstein, you only get one zeta. But in here you have two Eisenstein. So this object has depth 2.
Okay.
So there is a sort of hierarchy in terms of depths, but these objects themselves, they're not necessary. And as you go higher in depth, there is no reason to expect always to get a homogeneous solution to the Laplacian. Actually, if you insist that the Laplacian is the SL to Z invariant Laplacian. What is it? If you insist that the Laplacian is this one, just del tau, and you're asking for modular invariant solution to this one, that's it. Only Eisenstein series or some weird object which are called mass-cast forms. Those are the only things that you can actually find. Yeah.
And can we do this recursively? So, you have a new equation where the sources are the generalized Eisenstein?
Yeah, you can. However, this is something that we've been studying with Oliver Schlotter and Axel and many others. If you do these sort of games, not so much from the point of view of this integrated correlator, but from the point of view of string theory, low energy expansion, genus 1 and so on, you will see that in general, the source term, they cannot just be product of Eisensteins. You also need to use terms that are appearing at lower depth. So the story is much more complicated, yeah. But from the point of view of integrated correlator, so far we have only encountered these two objects, Eisenstein and generalized.
Okay, thank you.
Well, let's thank Daniele.
Thank
again.
you.